In this lecture, we will introduce another important concept in quantum computing, which is called measurement. In the previous lecture, we mentioned that a qubit can store infinite amount of states, which means that in principle, one could store every file in your hard disk in a qubit. However, this conclusion turns out to be misleading because of the behavior of a qubit when it is observed. Even though we can store infinite amount of data in a single qubit, how can we retrieve those data? Data is represented by a state in a physical system. So to retrieve those data, we need two steps. First, we perform measurement on the physical system to find out its state, and then we decode the state to the data. And measurement is very important in order to understand the configuration of the system. Let me tell you a story to understand better why measurement is important. Every day, Bob leaves a coin on the table to tell Alice whether he will want to have noodles or pizza tonight before he goes to work in the early morning. If the coin on the table heads up, this means Bob wants to eat noodles tonight. Alternatively, Alice should prepare pizza. After Alice wakes up, in order for her to find out what Bob wants to eat, you need to take a look at the coin. So Alice finds out that it is a head. The action of look at the coin is a form of measurement in order to retrieve the physical state of the coin. Alice may look at the coin for multiple times to double confirm her observation. The observed result will not be changed. She may take a look at the coin for the third time and the same result is retrieved. So Alice decides Bob wants to eat noodles tonight. Now suppose Bob wants to use a more sophisticated method to represent his preference. Bob used 0 state to represent noodles and 1 state to represent pizza. Now Bob initiates a qubit at 0 state. When Alice wakes up, Alice used a sophisticated method to obtain the state of a qubit, which is 0. And then Alice measures the same qubit again. She obtains 0. And then she measures the third time, is also obtaining the same results. So Alice decides to prepare noodles. As Bob knows that a qubit can store infinite amount of data, so Bob wants to store his choice of rice in the qubit as well. So he tells Alice that if she observes the qubit in the state of something like this on the right hand corner, then she should prepare rice. So today Bob prepared a qubit of rice, and then Alice performed the measurement. However, Alice observed the state 0. Alice performed the measurement multiple times and she still observed the state 0. Therefore, Alice prepared noodles. Bob made his preference on rice again on the next day. So Alice performed a measurement again. This time Alice measures the state 1. And then she measures multiple times and also observed the stage 1. Therefore, Alice prepared pizza for that day. So, this process is repeated for many days, and sometimes Alice observed the stage 1 and sometimes Alice observed the stage of 0. After 3 months, Bob found that about 70% of time he will eat pizza, and 30% of time he will eat noodles, and he never eats rice during the 3 months. So what happened? Bob is very curious, and he asks his friend Max Bond to find out the bug in their approach. And Max Bond listens to their story and find that first, why there is 0% of rice. He said that Bob did not understand some properties of quantum measurement. Suppose Bob set up a rice quantum state and Alice measured it and saw the state of 1. Then Max Born said that the quantum state is actually changed to stage 1, and this is called quantum collapse. Even though Alice measured the same qubit again, because the qubit has been collapsed, therefore the state will be 1, no matter how many times she measured it. Lastly, Max explained to Bob why he observed 70% of pizza and 30% of noodles after 3 months. Max states his recent finding about the quantum mechanic. Suppose we measure a quantum state phi, which is a superposition of n states. By Bond's rule, the probability of observing a quantum state J is the squared norm of the corresponding amplitude alpha J. So as Bob set up the quantum state of rice, the probability of observing 0, that means the noodle state, is the square of the square root of 0.3, which is 0.3. And similarly, to calculate the probability of observing the pizza state, we calculate it as the square of the square root of 0.7, which means it is equal to 0.77. That means there is about 70% of chance that Alice would observe pizza state and 30% of chance to observe the noodle state. And this explains the observation. So what is the right solution? Max suggests Bob to use 2 qubits. Use 00 to represent noodles, use 01 to represent pizza, use 10 to represent rice, use 11 to represent other food. Suppose Bob wants to eat noodles today. He sets the qubit to 00, and Alice measures it, and then we obtain the state 00, so that she will know that Bob wants to eat noodles today. Besides, using 2 qubits, Bob may save some time to decide what to eat tonight every day, because suppose he has a preference. For example, 40% of time he wants to eat noodles, 10% of time he wants to eat pizza, 40% of time he wants to eat rice, and the remaining 10% of time he wants to eat other food. So he may initiate the qubits using the same method every day, such that the two qubits is in this superposition of 4 quantum states. And then Alice measured it. She will obtain noodles state, pizza state, rice state, and other food state probabilistically. For example, after 3 months, on average, 40% of time Bob will eat noodles, 10% of time he will eat pizza, 40% of time he will eat rice, and the remaining time he will eat other food. So, Bob does not need to decide what to eat every day. Yet there will be some variation